Just hide the thing.
And our next speaker is Bhagya Subrayan. Hopefully I did not mispronounce it terribly. On ZTF. Let's go. Yeah, please take it away.
All right, so I hope people on Zoom, they're able to hear me. Let me start by introducing myself. My name is Bhagya Subrayan. I use she, her, hers pronouns. I am a graduate student, PhD candidate, working with Professor Mil Salvage at Purdue University. I take this moment to thank our workshop organizers, Gautam, for having me here, and then this is a wonderful opportunity to collaborate, network, and talk to people. Like, I really felt that I have been missing this out for 2 years in my grad school, and I'm really happy to be here. Okay, so I'll start with, and happy to share the work, what we have been working in our group with Refit. So Dan has given a brilliant introduction to Refit's ecosystem, but I'll just briefly go over through the first few slides so that the context and the motivation is set up. Okay, so since we are here, we all know why we are here, because LSST is going to be live soon in the coming years, and as a supernova person, it will provide me with a lot of opportunities for working with supernovae. Like, it will discover millions of supernovae. But the problem is that LSST data sets are going to be really, really huge. We can expect around 20 terabytes of raw image data, and which is approximately translating to 10 millions of alerts per night. And that's why we have like amazing, brilliant data brokers working on emerging technologies, software, and infrastructure that can help us promptly process these alerts and package it and give it to the astronomers like us, where we can do these sciences. So I'm listing out here, and there are a lot more coming up of data brokers that we use on a daily basis. Alerts, say Antares. Refit, as Dan mentioned, uses Antares data broker primarily, but we have all these data brokers which we look for, and each of these data brokers have unique capabilities on its own, and then they are emerging with different classifying methods and technologies. Okay, I know this is already done, but there is a need for a completely automated system where we can predict, prioritize, and identify what alert streams are of scientific value and trigger these follow-up. I'll just actually say we need to identify alert streams of scientific value and optimally follow them up, and I'll emphasize this point a lot in my talk. Okay, so this is already Dan gave a brilliant introduction for the ecosystem, and what I would be mostly talking about is the second step, where Refit is trying to predict and prioritize and recommend transients to observing agents. I really like the third step. It's because I know Dan did not go through this, but this step where recommendations are distributed to observing agents, it's curated to them, and he really did miss the point that it is it's based on what telescopic facilities they have, and it's like a Netflix where you have Netflix recommendation system where you are having recommendations to you based on your choices and interests. And he mentioned that point, but I really wanted to emphasize that point. And then once observers trigger their follow-up or get their recommendations and act upon them, the data is recycled back, and then to the Refit ecosystem, it predicts and prioritizes and make better predictions with the data which it already has. So I'll be talking about the forecasting system mostly in this talk. So here is an example of a ZTF event which is currently live. So each alert is corresponding to the difference imaging between the science image as well as the template image. So it's the difference imaging which is here. So Refit in its core currently has data-driven forecast. And what do I mean by that is that it references events from its trained reference library, and it tries to have vector representations similar to the current live event. And the forecasting part is done by matching the phases of these events to the current live event, and then using Gaussian process regression on the reference library events to predict a forecast. Now, here is this is currently live event now. So this is the data-driven forecast predicted by Refit in two bands, ZTF bands, basically ZTF-G and ZTF-R. Now, my question, or the question I am trying to address is, in this work, is a different type of forecast. Data-driven forecasts are great. They also give us a lot of information. But what if we are able to recognize our forecast based on the underlying physics of each of the transients? So the work which we focus in this talk is about CoreCollapse supernovae. We are focusing, and I consider this talk to be an idea, and this could be extended to multiple different types of CoreCollapse supernova. So those are the questions which I am trying to address, is like, can we have the forecast driven by our underlying physics of the transient, and then can we use these characterizations as they evolve to guide the follow-up of these transients. I forgot to mention about the other efforts for follow-up, like the Marshall system, as well as the target and object managers, where they help to help observers to plan what they need to follow up and help them follow that up. Okay. Before I go into the inferencing part itself of how we are able to characterize supernova transients as they evolve, specifically CoreCollapse supernova transients, I would like to highlight what are the challenges that are involved in this process. So I would like to get your attention to 2 points here. So here is a well-sampled type 2 CoreCollapse supernovae, which is bright and nearby. It is 2014 CX. So this has all the densely sampled data set, as well as multiple wavelength coverage. But if we compare this to the survey like this, which we are going to expect from LSST, ZTF, we are already knowing that this is an issue. With LSST, it's going to be even more worse. So the data from surveys are going to be having a lot of missing epochs, not unconstrained peak time of explosion. All these I rushed fast. All these 4 points which I mentioned is like we are not having the best data quality from all sky surveys. So it is traditionally what you would do is like you take these well-sampled data set, construct a bolometric light curve, and then try to fit models to it. But that's not possible with survey data because you have insufficient filter coverage, you do not have measurements at the same epoch, so it's really challenging to do the normal traditional way of constructing bolometric light curves and inferencing explosion properties or progenitor properties of these supernovae. The second point I want you guys to take home is that is it really necessary that we have so much data for a single event? No, because all the data which is available for that event is not equally valuable. But in case of surveys, this is too sparse for somebody to actually infer something from these light curves. So what we need to have is like augmented, we have to augment photometry so that we have optimal data coverage so that we can infer science from it. So LSST, instead of just being a discovery machine, it is just, it is nice to have optimally augmented CoreCollapse supernovae samples, or generally any transient sample, so that we can have population studies on that and we can have characterization of those events. So it's not just being a discovery machine. It is great, a discovery machine. We are going to expect things which we have never seen before, but to make the scientific value of these surveys, it's important that we have optimal data quality so that we can characterize them and get physics out of them. So in the effort, we started by characterizing complete light curves of CoreCollapse supernovae from ZTF light curves. So the ZTF has publicly available photometry in ZTF G and R bands. So we took those data, and then these are spectroscopically classified type 2 supernovae. We used hydrodynamical modeling for fitting these events. And then I will in the next slide, I will talk more about those hydrodynamical models. But then basically what you're fitting for is the progenitor properties and explosion physics. In addition, we are also fitting for host extinction and the explosion date. One point to mention here is that surveys are great places where we can leverage the upper limits. So what we learned from this study is like when you're fitting for explosion date, you're leveraging the information from the upper limit so that you can have an informed prior distribution for this. By the way, the model fitting is based on Bayesian inference. So each of these parameters will have a prior distribution, and then we are trying to compare it with the data which we see with a likelihood function. So we developed, and it's unfair to say that we developed. This has been in the literature where you have a grid of hydrodynamical models of varying ranges of parameters, and then you interpolate between these models so that if you have a sampling method in place for any combination of parameters, you have a value within the interpolated within the grid of the models. So here I'm showing the first 15 light curves or like characterizations of ZTF events. If you want to have more fun with these plots, I can show you more plots. It's in the reference slides. I just wanted to have show an example here. So some of them have, oops, I am referencing the wrong, okay. Some of them have upper limit prior to the first detection. So with respect to the upper limits, the explosion date fit here is with respect to the first detection. So we use or we leverage these upper limits prior to the first detection to get an informed to have an informed guess on the prior distribution for explosion date. So the best fit model, I don't know if you can see it clearly, but the solid line is the best fit model, and these are like samples drawn from the posterior distribution. Okay, so diving deep into the physics, what are these hydrodynamical models actually made of? So these are red supergiant pre-supernova progenitors, which were evolved using Kepler, and then we have those taken and then evolved using radiation hydrodynamics using Stella. So a big shout out to our collaborator. I did not mention the name here, but I have to say it. Professor Takashi J. Moriya, he is a collaborator in Japan. He is the one who is providing us with these synthetic model light curves, which we can compare to the data from this ZTF data. We also incorporate a CSM structure to these hydrodynamical models, so a steady acceleration wind as well as a mass loss rate. So these two are parameterized with these two parameters. The others are progenitor properties, and then the rest of them are like explosion physics. And these two parameters are the ones which we additionally fit. And as I mentioned, the prior distribution is taken away by, prior distribution is narrower for the ones where we have well-defined upper limits or we have a good rise time data quality, but it reflects in the fitting or the inferences that you make if you do not have them, and I represent that here. So this is a correlation plot between the different parameters, and we compare it with other works. So Foster et al. 2018 and Martinez did a similar kind of work, but in different scenarios. So Foster et al. They did using the data from high cadence transient survey, and Martinez did it for in general using hydrodynamical modeling for a well-sampled type 2 piece from the Carnegie Supernova project. So we tried that. We tried if we can inference the complete light curves first with the ZTF photometry, because it's a survey data and we were not sure how good we will be able to do it. But once we were able to recover these inferences, we had very good discussions with Thomas Mathieson from Noir Lab. He brought the idea about, hey, why don't you just fit these light curves as and when how they are evolving, and then see how these parameters change. Okay, some other things that I wanted to mention here. So this is not a perfect project, so we are limited by certain the things which I'll be talking about in our limitations. So we are actually limited by the model boundaries. So the gray lines in these plots, actually they refer to the model bounds. This is an additional parameter that we fit. So the model bounds are actually relevant for the explosion physics and ZAMS and progenitor property parameters. And if you look at closely here, Martinez et al. They had a linear kind of correlation, but from our inferences, we find some of the events having overdensity towards the model boundaries. So we are less confident in those inferences. Okay, I'll talk more about this, but the takeaway is okay, we can do this for all the survey all the data for complete type 2 supernova light curves. Why can't we do this for as and when a supernova is evolving? So this is a animation where I show how this is for a ZTF event. So as and when the data is evolving, how the parameters are changing, and this is for all the parameters that we fit for. So this is a 10-day cadence. So you take the data from with respect to the first detection for 10 days, for 20 days, for 30 days, and you go, and then this is how the parameters evolve. So I'm a little rushing towards because I have 4 minutes. Okay, so this is how what we learned from how the parameters evolved. So initially we found that so just to guide you through the plot. So this is each data point is a difference between the first inference. So we found that there is no value in doing every 10-day inferences, so we just made it into like every 25 days so that we can have a general trend of how, when the data comes in, the models are evolving. So what we found is that initially some parameters are underestimated while some parameters are overestimated. For example, for nickel mass, initially it's underestimated, and as and when it evolves, it's overestimated. And this is for all the 45 events that we have. So it's like averaged over all the 45 events. So for energy instance, these events, it's initially underestimated, but then, sorry, it's initially overestimated, and then towards as and when all the data comes in, it is underestimated. So this is how parameters evolve, and I'll be happy to talk more about these if you want, but I really want to take the point that this method or this ideology can be, this idea can be used for inferencing live events. So for example, this is an example of 2 ZTF events which are currently live, and these are the parameters which we used. So these are the parameters that we model and we got from the hydrodynamical modeling. As I said, there is discrepancy, like the time of explosion, this has no defined upper limits, whereas this has upper limits, where, so it's much well constrained, I feel. So I would say that I would be more confident in this inference versus this inference. Yeah, so yeah, this is the slide which ties back into Refit. So why do we need such an inference system? So it goes back to the point that we can prioritize, and we can also identify epochs where it is necessary to optimally sample or augment, sorry, not sample, optimally augment data so that we have, we can allocate resources to other transients at the same time. So we do not need to oversample a particular light curve, but we can identify information-rich epochs where we can guide the observing agents to follow it up. So here is the progenitor. So it helps in developing prioritization. So if you want a particular parameter, desired parameter space, you can just say, hey, we need this scientific objective. This is our scientific priority. And then Refit would recommend you the targets which fall into those scientific priorities if the characterization is done as and when ZTF light curve evolves. This could be done with YSE experiments, YSE experiment 2. This was publicly available, so we used the ZTF data as and when. And going back to Alex's point of detecting anomalies, how do you detect anomalies with it? It's in the next slide, but I just want to make one more comment here. So as Dan mentioned, so this is all about coordinating observing resources all around the world. So what if we identify here, for example, we identify this epoch where it's dropping off for a type 2P. Now, what if this is not observable with ZTF? You can always call your southern observers and say, hey, we don't have access to any of this. Can you observe this for me? So you're identifying information-rich epochs and coordinating worldwide observing resources to follow up survey events. We are spoiled by ZTF. LSST, it's going to be even worse. So the actual value of this comes with very less photometry available. Okay, so coming back to your point where there is anomaly detection, so this would be with reference to this specific type of class. So we would be able to identify events which completely do not fit, but there is a caveat here. Currently, the models are only with the given parameter ranges which we have, so we are extending. So our model fitting would think that this is the best fit model, but it actually is not, because we can always explore more parameter space. So traditionally, things that deviate from the normal type of supernova in its characterization would be tagged as an anomaly, and these could be flagged, and Refit could identify and send recommendations to observing agents to follow them up. Okay, now I think I have touched on more points, but these are some of the takeaways, and I'll just wrap up in a moment. So creating synthetic model light curves in their survey passbands is much more powerful way to catalyze on-the-fly characterization compared to bolometric light curve. And we have thought a lot about this, and I think this is some point that needs to be taken away to have an on-the-fly inferencing for ZTF events. And LSST can only provide us with photometry, and then the inferencing and subsequent follow-up can enhance population studies. So if you have optimally augmented photometry for type 2s, you can have a population study for them and analyze in a similar way. Okay, now I feel like any project is will have limitations, and there's always scope for improvement, so that you can work more on it. So I'll just outline here the current limitations as well as the future work. So there is, this is a known problem for type 2 supernovae. It's like degeneracy in parameter space, which means like there might be multiple combination of parameters that can lead to the same light curve which you see. So how will you be confident in your characterization? It's still a problem, so one way to do or not get away, one way to try to solve it is like to incorporate velocity information, but that's also going to be challenging with LSST coming in, because we don't know how many spectroscopically classified supernovae would be there. So this is still a work in progress. We need to think of more ways, and if anybody has ideas, please let us know. We'll be happy to incorporate. And then, oops, God, I always change the button. Now it's limited to like a limited range of parameters. We are always trying to extend the parameter space so that it can, the events which were limited at the boundaries, it might be actually having a lower value or higher value, but we'll be actually able to work with all those things if we have a larger grid of models. And then now it's limited to spectroscopically classified type 2s, but Patrick's talk as well as David's talk, we have photosy classifiers which will give us photosy, so that can be incorporated and tested in the system. Yeah, and this can be ultimately incorporated on a nightly basis to Refit so that we can choose with what scientific priorities we have. And it can be also extended to other types of CoreCollapse supernovae if we have a good working set of hydrodynamical models. I think I'll leave it at that. Thank you for listening to me, and I'll be happy to take any questions.
Thank you very much. So we have time for about 1 or 2 questions. Please raise your hand, either on Zoom or on, yeah, Nikki Arens.
Thank you so much. I was just wondering, as you're going to expand it to other supernova types, how would you deal with, if you're uncertain in the beginning what type it is, how would you then make simulations of the continuation of the light curve?
Can you repeat the question? Sorry, I didn't.
Yeah, if you're in the beginning not sure which type of supernova it is, how would you then use these simulations to extrapolate the light curve?
Great question. Like, this is a work which is limited to type 2s. So for example, Refit is data-driven though, so it does not. It also gives a classification to it. So if classifiers are able to predict what type is, we can always test this. So with LSST coming, we would be relying. It would be a conjunction of this idea with photosy classifier, so that a classifier can say, hey, this might be a type 2, and then you can always start inferencing and see if you get reasonable parameter spaces. Does that clear? I hope I answered your question, but that was a great question.
Yes, yeah. It is clear. Thank you so much.
All right, I move to one on Zoom. So we have Anirban, please, go ahead.
Yeah, hello. So it was a very nice talk. I wanted to ask, like in your slide on hydrodynamical model grid and parameter space, you have defined some priors as uniform and some priors as normal or something. So can you shed more light on like how do you choose the priors to be uniform or even Gaussian priors or something? Like, do you have any sort of ideas before and something like that?
Thank you for the question. Trust me, I have thought this myself. Why did I use? But two parts of answer to that question. One, there are similar works, so your priors could be inspired from their work and see if that works for your modeling. But the second thing is that you can always try both the priors and see what works. If it is having any significant difference in your inference, just if you do that analysis, and this was the one which was working the best for us, so that's why we choose those.
Okay.
Thank you for the question.
Okay. Thanks.
All right, so the more questions, please ask her either in person or on Slack. The conference is going on for another 3.5 days. And so let's thank again.
Thank you.
Oh, yeah. And our last speaker for this morning,